and today's speaker is Alexander Buфетов, who is a member of Steklov Mathematical Institute and Aix-Marseille University. And the title of his talk is Point Processes and Interpolation. So let's start.
Okay, thank you very much. So let us start with formulation of main result, which is joined with Borichev and Alexei Klimenko. So we will consider the sign process. We'll consider the sign process. I will give detailed definition slightly later, but for the moment we consider just this infinite configuration on R, and so it is a result of Gauche that this configuration is uniqueness set for Paley-Wiener space. For Paley-Wiener space, let us recall that Paley-Wiener space is the space of functions whose Fourier transform lives in minus by pi. Okay, so just this set is a uniqueness set for this space, and the question is whether it is possible to reconstruct explicitly Paley-Wiener function from this space. So just the question is that of unique reconstruction of a function in Paley-Wiener space from this from its restriction onto this configuration. And unfortunately, we are not able to reconstruct uniquely the entire Paley-Wiener space. In fact, we will have to consider the subspace. So we have to fix M0 sufficiently large, and and zero sufficiently large, and consider the subspace Paley-Wiener minus M0 of functions which decay at infinity faster than x to n0. So it is useful to maybe rewrite like this. So it is useful to observe that multiplication by x, if it does not take us away from L2, it also does not take us away from Paley-Wiener space. So, in fact, Paley-Wiener space is preserved. One can see this by looking at the definition of the Paley-Wiener space in terms of Fourier transform. In fact, multiplication by x in Fourier transform is differentiation, and If function, derivative of function is in L2, then so I should write f in L2. If derivative of function is in L2, it automatically has support from -pi to pi. Support of derivative cannot increase. Okay, so now just this function, if it does belong to L2, it belongs to Pellinger space itself. Okay, so we consider this subspace. It is dense subspace in Pellinger space. F is in Pellinger space. Write it like this. F is in Pellinger space. Okay, and just this is the definition of the space. And then the claim is that it is possible to reconstruct function from this dense subspace using Lagrange interpolation formula. So what do I mean by Lagrange interpolation formula? What do I mean by Lagrange interpolation formula? So let us consider, let us assign to this set, so entire function, it is possible to assign to this set entire function, so let us denote this set X, so X subset of R, X subset of R. It is possible to assign to this set an entire function. So which one? The following. It is essentially Weierstrass product, except we don't need the exponential terms. We don't need the exponential terms. So I just write GXT is the product over X in X. So I use X capital for the configuration and X small for the particle for the configuration. So X in X, 1 minus T over X. So this entire function assigned to the configuration is the main character of the story. Is the main character of the story. Okay. So now, so we will recover our function from not just uniqueness set, but from minimal uniqueness set. Let us recall. So again, theorem of Gauche says that realization of psi process is uniqueness set for Pelli-Wiener space. It does not, however, say that it is a minimal, that it is a minimal set, that it is a minimal set, that it is a minimal set. So in fact, there is a subtlety here. So let us recall that uniqueness set is set such that every function from my Pelli-Wiener space in restriction to this subset, if it is 0 in restriction to the subset, then it is 0 identity. So the function is uniquely determined by values of its restriction to this subset, So this is what I mean by uniqueness set. So just minimal set is uniqueness set such that if you remove one point, it no longer is uniqueness. So it is not clear, a priori, it is not clear, and in different examples, in particular in examples of determinantal point processes on Lobachevsky plane, it is the corresponding trajectories, the corresponding realizations have infinite infinite excess. That is to say, even if one can remove, if one does it in an appropriate way, one can remove infinitely many particles and the set will still be uniqueness set. This is not the case for Penny-Wiener space and for the sign process. So the sign process has access 1, and if I remove one particle from the sign process, then the resulting set is complete and minimal. Complete and minimal. Okay, so let me immediately remove this particle, GX. So X without P, so P is arbitrary fixed particle. P arbitrary fixed particle. Fixed particle, fixed particle. Okay, and just this set, X without P, is complete and minimal set. Complete and minimal set. Complete and minimal set.
Hello, Sasha. Hello.
Yes, yes.
But P doesn't have to be inside X almost surely.
No, I take P inside X. P is particle in X. In X. In X.
So P is you mean P is a random set, random point.
No. P is particle in X. I choose some particle in X.
Okay.
X is random set. I choose arbitrary particle. So the function. No, let's be very clear on this point. There is same question also in the audience. X is arbitrary. X is random set. I take random set and I choose one particle. I can choose any particle. Please observe that if I choose different particle, the fact of being complete and minimal doesn't change. The fact of being complete and minimal doesn't change. If I remove not this particle but that particle, it doesn't change. Okay, any more questions to this point?
Sasha, just a comment. All what you wrote after this product is really hard to read.
Which one? So
in your last line, you use the formula and then some rectangle.
Okay, so I write bigger. Okay, so here let me just say in words that it is just infinite product with one linear multiple removed, and this is what we are considering. Okay, so now this set, the set X without one particle, is complete and minimal set. So if I remove one more linear multiple, then the resulting function will be in Penny-Wiener space. So let me consider now this function g x b divided by t minus q, where q is a different particle. Q is an x without p. X without p. So yes, so this function already belongs to Penny-Wiener space. This function belongs to Penny-Wiener space. So, and these functions are analogs. These functions are analogs of expressions that enter in the Lagrange interpolation formula. So this function, so let me denote it by GQX of t. So now I'm ready to formulate the main result. Okay, let me erase the definition of Penny-Wiener space. We are already familiar with it. And so the main result is that the function f is equal to the sum over q in x without p GQ over GQ in Q. Okay. And the sum converges, because f of q decays sufficiently fast. F of q decays sufficiently fast. So this is what I mean by Lagrange interpolation formula. So this function, let us observe that the function GQ, so let me write here x to stress the dependence on x, functions are functions of the variable t, GQx or t. Okay, so GQ over GQQ obviously is equal at point Q is equal to 1. And let me write it like this, at different part x is equal to delta x cubed, where delta is the Kronecker delta. So even I myself on the blackboard on my screen, I can see the formulas. Is it possible to read the formulas? Alyosha?
More or less possible.
Cool, okay. Very good, thank you very much. Okay, so these functions are functions which are equal to 1 at each particle, at the particle Q of my uniqueness set. They're equal to 1, and at all the other particles, they're equal to 0. At all the other particles, they're equal to 0. So at the particle Q, they're equal to 1, at all the other particles, they're equal to 0. So in fact, it is just the Lagrange interpolation formula. I interpolate the function through its values in this bi-orthogonal system to the system of reproducing kernels in my complete and minimal set. So bi-orthogonal. So this system is bi-orthogonal to the reproducing kernels. So in fact, just by definition, because the value of each function at each particle of configuration is 0 except the value at the function q. And this is how I recover my function f, and this is the main result of the talk, joined with Alexander Alexandrovich Borichev in Marseille and Climenko in Moscow, and of course we wanted to put it on the archive before the talk, but in fact it will happen after. So this is the main result. In fact, though for simplicity of exposition, I limit myself in this talk to Pelley-Wiener space. Maybe I will briefly mention other examples later. The result itself we obtained for several classes of examples. In particular, our result also applies to space with air kernel, Bessel kernel, and also we are able to go beyond uniqueness sets which are limited to the real line. We are also able to prove the same result for the Fock space. We're also able to prove the same result for the Fock space. Okay. So one should say that the result that I quoted saying that the set, the trajectory of sign process without one particle is complete and minimal set, this result is specific to the Pelley-Wiener space. This result, I don't have it for general spaces. So for area and best set, I only have estimates that the axis is at most 2, at most 2. So, and for fog at most 3. So I only have estimates. So if I remove, excuse me, I misspoke. The axis is at most 1 for area and best set, at most 2 for fog. So if I remove 2 particles for area and best set, then it is already not a uniqueness set. But I do not know whether if I remove 1 particle from area and best set, is it uniqueness set or not uniqueness set? Whereas for fog it's the same, but I must remove 3 particles, and then it's not a uniqueness set, and whether I do or do not obtain uniqueness set by removing 1 or 2 particles is open question. I don't know the answer to this question. At the same time, I do know that the set, the uniqueness set in all these cases, in all the cases, the uniqueness set has finite access. This is very important for the purpose of this talk, that uniqueness set has finite access, and having finite access, I can remove some number of points, and then it becomes a complete and minimal set. This number of points does not depend on realization, because this number of points is a tail characteristic of the trajectory, and determinant point processes have trivial tails in algebra. So I can, by removing finite number of particles, so 0 or 1 in this case, and perhaps 0, 1 or 2 in this case, obtain complete and minimal set, then the definition of the subspace is the same, and the result is exactly the same in all these cases. And the proof is also the same in all these cases. The proof is also the same in all these cases. Okay, now let me speak about the proof. If there are no questions about formulation, any questions in the audience? If not, let me say a few words about the proof. Okay, so let us recall just the sign process is obtained from the Gaussian unitary ensemble on Hermitian matrices. So I consider Hermitian matrices and endow them with Gaussian measure. Then, by the semicircle law of Wigner, the eigenvalues of these matrices almost surely belong to an interval of length square root n. So square root n. The distribution of these eigenvalues is dictated by the semicircle law. So the observer places himself at the top of the semicircle, and then since there are n eigenvalues on an interval of length square root n, in order to obtain distance 1 to the closest eigenvalue, the observer must rescale by square root n. Must expand by square root n. Okay, so expanding the eigenvalues of the Gaussian unitary ensemble, so the Gaussian measure on the space of n times n matrices expanding the eigenvalues by root n, we obtain point process, which is precisely determinantal point process with sign kernel. So this is the sign kernel, and the correlation functions of this process are the determinants of the sign kernel. This determinantal structure is key element of all the analysis that follows. This is the determinantal structure. Okay, so this is the sign process. So, and the key element, the next key element of the analysis is the following analog of this property for the sign process. So the sign process is not a Gibbs measure, but almost. And so this is precisely what I'm writing now. So I will describe the conditional measure of the sign process on some interval I when one fixes the exterior of the interval. So this is fixed. And I'm interested in the conditional measure of the sign process in this interval. So it is a very beautiful theorem of Gauche and Perez, that the number of particles in this interval is fixed by the configuration in the exterior of the interval. In fact, by the way, I should say it is possible to approach the theorem of Gauche and Perez by relating it to 1941 paper of Kolmogorov. So where Kolmogorov is interested in interpolation for stationary processes. So to point process one can assign stationary process just by computing to stationary point process one can assign a stationary process by computing number of particles in successive intervals, and then Kolmogorov gives necessary sufficient conditions for the fact that the zeros component of the stationary process belongs to the span of the other components, which precisely implies the theorem of Gauche and Perez in the stationary case. And this is an approach we took in joint work with Shu and Komorowski. But just one should say that the argument of Gauche and Perez does not, as opposed to the argument of Kolmogorov, does not explicitly use stationarity. It's an L2 argument, but not based on stationarity. In any event, the number of particles is fixed, again, using the result about the fact that realization of sign process is complete and minimal with one particle removed. We can say exactly how many particles are here. We can say how many particles. So here, this is the configuration fixed outside. How many particles do I need to put here? Well, I need to add particles until I obtain complete and minimal set. So if this set is already complete and minimal, then I add one more. So I add particles until I get complete and minimal set, and then one more. So if this set already has access 1, then there is nothing to it. If this set has access more than 1, then such event has probability 0. So there is nothing, so it's already too many particles. If this set has infinite access, this is again event with probability 0. If this set has defect 17, I need to add 18 particles. So I need to add particles in order to obtain complete and minimal set, and one more. And one more. Okay, so and one more. But now the question arises of conditional distribution. Conditional distribution of these particles. Conditional distribution of these particles. So, and this is exactly what I'm going to write here. So, conditional distribution of these particles is orthogonal polynomial ensemble. So these are fixed, we remember this. So the conditional distribution is orthogonal polynomial ensemble.
Sorry, I have a question.
Yes, of course.
It seems to
Just speak loud, otherwise it's
it
impossible.
seems to me that conditional measure zero. Yeah.
Well, of course, it's conditional expectation with respect to sigma algebra, of course. It's, I'm describing, that's quite right. I'm describing conditional expectation with respect to sigma algebra. So conditional measures on fibers of this partition in sense of problem. Yes. So precisely, yes, yes, exactly. That's quite right. Yes. So I take, so I have orthogonal polynomial ensemble, and then the weight is precisely this function, and this is the key point, with finite number of particles removed. So I write it explicitly, product 1 minus ti over x squared. So ti are the particles inside I, t1, and so on, tn. Okay, so the product is double, both in. So is it possible to see, Alyosha, is it possible to see the last slide or not so much?
Yes, it's possible.
Okay, good. Okay, so here I have I less than j. So there is renormalization also. And this is the form of the conditional measure of the sign process, conditioning on fixing the exterior of fixed integer. Conditioning on fixing the exterior of fixed integer. And this is the key element for the proof of the result. The key element for the proof of the result. So in fact, let us look more attentively. At this expression. So another key aspect of the analysis is that determinantal processes, this is quite a general property of determinantal processes, determinantal processes are negatively correlated. Determinantal processes are negatively correlated. So particles in, what do I mean by negatively correlated? I say quite precisely. Adding a particle at one side decreases the probability of a particle at a different side. So particles don't like to be together. They repel each other. Intuitively, this is clear from description in terms of eigenvalue of a matrix. It is clear that, in fact, it is extremely improbable that a matrix, for example, an Hermitian matrix, have multiple eigenvalues. So it is extremely improbable, and so, in fact, particles repel each other. At the same time, this intuition might be misleading because, for example, if instead of, so this property of repulsion is specific to determinantal processes. So determinantal processes have a cousin, Pfaffenberg processes, which also correspond to eigenvalues of matrix, so not Hermitian but orthogonal or symplectic matrix, except Pfaffen processes are not negatively correlated. Pfaffen processes do not have the property of negative correlation. So determinantal processes have property of negative correlation, Pfaffen processes don't. So this is property very specific to our model. It is possible that it can be weakened and the result can be formulated also in more general setup, but let me tell the proof which I can prove. So explain the result which I can prove. Okay, so the determinantal processes are negatively correlated, so it is quite improbable, it is extremely improbable that there are many particles in one fixed interval. So in fact, the next step of the analysis, so in this sum, we need to analyze, all the terms. So the function f decays sufficiently fast. It is not the most difficult thing in the world to see that this expression, GQX, which is written here, GQX does not grow too fast. The GQX does not grow too fast. It is not very difficult. So precisely because the particles don't accumulate too fast. So it is possible, there are many ways of proving it, but it is possible to prove that there does not arise a situation when there are too many particles at once. Okay. So the most subtle point of the analysis, so far everything has been rather straightforward. So the main difficulty in our analysis is the analysis of this, of the denominator. So the denominator, in other words, it can be seen, well, one can see from this formula, it's the derivative of Jx. The derivative of Jx at a0. The derivative of Jx at a0. So, and this is precisely the subtlest point of the analysis. This is where we cannot just use naive estimates of the form that there are not too many particles here and there. And just this is precisely at this point where we use this description of conditional measures. So the description of conditional measures is used precisely in the estimate of this derivative. I need, in order to ensure the convergence of the sum, I need that the derivative not be too small. So 1 over the derivative not be too large. So the estimate which I need, the estimate that I need is something like this. GQQ is greater or equal than norm of Q minus N naught. So this is the estimate, this is the key estimate. And it is precisely for this key estimate that I need the characterization of conditional measures. So in fact, the characterization of conditional measures characterizes this. This is the key point. How do I say? The key point of the specificity of the analysis. So far, let me point out that so far I have not used anywhere that my realization is realization of the determinantal process. I have said that particles don't accumulate, that particles repel each other, but I have nowhere used in fact the determinantal structure. So now comes the moment when actually I use it. So I use it here. And the corollary is, let me erase it right here. The main point is that the expectation, so it's essentially a reformulation of this statement. So the expectation with respect to bound measure at some point, let's write point P, of the expression product, so of the expression Gx without P at Q Gx without P at P. So this expectation in square is equal to 1. Because in fact, this ratio is precisely the Radon-Nikodym derivative, excuse me, the Radon-Nikodym derivative of bound measures. So precisely, please observe that describing conditional measures just by application of theorem of bias, so describing conditional measures, the conditional distribution, fixing, so by the way, I come back to your question again. So describing conditional measure fixed exterior and conditional measure interior is the same thing by Bayes' theorem as doing it the other way around. So fix, change interior, and what is the impact on the exterior? So in other words, take palm measures, so conditional measures by fixing particles, and what is radon negative derivative between these palm measures? What is radon negative derivative between these palm measures? In fact, because of rigidity of Gaussian pairs, palm measures are singular with respect to the original measure. So this is, if you wish, extreme opposite of the what's called the bus parallels. So here palm measure is singular with respect to the initial measure, as opposed to Poisson process where take palm measure, not take palm measure is the same. So it is singular with respect to the original process. So at the same time, different palm measures are equivalent. Different palm measures at different points are equivalent. They're different. In fact, it is especially simple if one thinks about orthogonal polynomial ensemble. So what does it mean, palm measure of orthogonal polynomial ensemble? It's just precisely one needs to multiply by the product of weights p minus x squared. Well, this is exactly what's written here. This is exactly what's written here. So radon negative derivative of palm measures is the same as for orthogonal polynomial ensemble. So, and this is exactly the key point, and this is why I have this equality, so that just radon negative derivative, radon negative derivative of palm measures is precisely the square of this function. So the expectation of radon negative derivative is by definition 1, because it's radon negative derivative. So the expectation of this quantity is 1, but this is precisely what we want to estimate. So by choosing a not sufficiently large, we can invoke just very naively Borel-Cantelli lemma. So this is why we're able to obtain this estimate and prove the theorem joined with Alexander Alexandrovich Borychev and Alexey Vladimirovich Klimenko, and thank you very much.
Okay, any questions, comments?
Hello, Sasha. Hello?
Hello, yes?
Yes. So I want to know that. So wait. Suppose
Yes,
now.
yes.
Suppose now I have a minimal complete set, and I can prove with some method that this series indeed converges. Then whether this identity is automatic, if we already know that
it's uniqueness set. Yes, of course, because it's uniqueness set, actually. Yes, thank you very much for the question. Thank you very much. I did not say this explicitly. Yes, because it's uniqueness set. Let me point out to you different points. So in fact, where did I use minimality? Where did I use minimality? So in fact, precisely where you asked me, because the proof that I explained works whether or not the set is minimal. Please observe, however, that if the set is not minimal, then this function is maybe not even in L2. So this statement written formally, let me put it a different way. This convergence written formally, it holds. But then maybe more effort is needed to prove that the equality that you mentioned, that the limit is in fact the function.
Okay.
Yeah, so because I can prove this even if these functions are not in L2, I know where used they are in L2. The fact that they are in L2 is precisely where minimality comes into the game. Also, by the way, I should say, now that you asked it, I should say that I was a little bit imprecise. I did not spell out all the details. convergence of this series, pointwise convergence of the series in L2. There are some subtleties here, but since precisely, the delicate point would be to try to find smallest N0 for which our result holds. But we don't ask this question. So if you allow yourself to take bigger N0, then you can always ensure the convergences in L2, convergences in every conceivable sense. So, but if you wanted to say N0, let's say equal to 3, that would be a completely different question, which I cannot answer, so I ask it to the audience. So how to make small N0? This is, we don't have result about that.
You don't have results like partial results? Not even partial results?
No, nothing, no estimate. No, well, I mean, some naive estimate, maybe some naive estimate one can get. We don't use a lot, but no. I mean, we just, for example, here, I mean, one can probably say N0 equal 10 or something. But
yes, but if N0 gets smaller and smaller, can you estimate the excess of at least, can you...
Sorry, say again?
The excess,
Of what? Of what?
Of the process, I mean...
Yes, of course we can. No, excess is 1. Excess is 1, and for these ones at most 2, and so on.
Yes, but for big N0.
For a second?
N0,
no, just a second. Adrian, excess does not depend on N0. Excess is for initial space. Yes, but this is dense subspace. It's dense subspace. No, this is also, thank you very much for this question. It is important to keep in mind. No, but in fact, maybe this question emerges because, in fact, if you think about space of polynomials, such space would not be dense subspace. So please observe that there is important difference between our space and space of polynomials, namely that the functions, so reproducing kernel has integrable form, AB minus BA. But the functions A and B themselves are not integral. So they will be sine and cosine for polynomial space, or Bessel functions for Bessel kernel, or Airy functions. They're not themselves square integral, as opposed to case of polynomials. So this implies, this follows from the work of Schmidgen, this implies that very old work, Schmidgen, from the 80s, I think more or less as old as I. So just that the space, this one is dense. The space EWN0, well, for polynomial itself, it's more or less obvious. But for very general reproducing kernel spaces, the space is dense. The space is dense, so it's dense of space. It's dense of space. But interpolation formulas, they depend on subspace. It's not, you cannot pass the limit in interpolation formulas.